Okay, so recording has started. Okay, good morning to all of you. So in the last class, where we have ended, during the last part of of the last class. Actually, we are discussing about demultiplexer, right? And we have seen like how we can use and decoder as an demultiplexer, right? So for decoder, we have an enable input. If the decoder has an enable input, right, and it has this input. So, but for demultiplexer, this input becomes the selection line, and this enable input that becomes the actually the input. Okay, the input, right, through which you will pass your data, and depending on the selection line, this data, what is present in this enable line, that will be transferred to either one of this, either D1 or D not D1 or D2 or D3. That will depend what is the value of this selection line. For example, if the selection line value is 00, then this data will be transferred to here. If this data selection line value is 01, then it will be transferred to D1. If it is 11, then this data will be transferred to this D3. Okay. Now, yesterday you had some doubt on this, so I thought let us concentrate, let discuss a little bit more. Okay, with an example. For example, see basically what is this demultiplexer? So demultiplexer, basically this is written as F, so you can consider it as like E, right? This is that enable input for us. Okay, on here you will apply your give your data. Okay, right. So depending upon the value of the selection line, this data will be transferred to either one of this input, either one of this input. For example, when this data value is 00, you see this data will be transferred to the first one, right? When this is 01, it will be transferred to this B, right? From here. When it is 10, it will be transferred to this C. When it is 11, it will be transferred to this D. So you can also assume the this system as something like this. Right here it is y0, y1, y2, y3. I think for one of you, this is your microphone is on. Okay, so yeah, thank you. So here you can see this is the input. Please check. You can still hear me.
Yes, sir.
Okay, thank you. So this is the input, and this is for the output. So you can also assume it like this, that here you have these two selection line, selection line by giving proper value. So it has this input. So input, this arrow can be connected either with this or with this or with this or with this. So this is basically the demultiplexer. That means depending on the value of this selection line, whatever the data is coming through the single channel, you can deliver that data either to one of these, yes, okay, four members, right? You can deliver it. So this is basically a demultiplexer. Now let us consider one example and see how we can actually make the circuit. Okay. So for the time being, let us consider this one. We need some space here, and we want to continue it in a single page. So I made some space here. Okay. So let us consider this 1 cross 4 DMUX. So DMUX means basically stands for demultiplexer. MUX stands for multiplexer. Right. So how does it look like? So it's basically will be in a if you want to draw in a type of box shape, then it is something like this: 1 cross 4 DMUX. How many selection lines will be there for this?
Two.
2, because we have one input that is given here. So this input is 1, output is 4, and selection lines are 2. This is the output and this is the input, right? We have to design this circuit. Okay, so for that, let's say the selection lines are like this: S0 and S1. Okay, and input is the data input, so we are representing it as D. Okay, and this output we are saying then giving the names as this Y1, Y2, okay, Y0, Y1, Y2, Y3. Right. So again, we can draw the truth table because we have to arrive to this like final circuit. So the truth table for this would be, let us start with the selection line, that is S1, S0. These two are the selection line, right? Then D is the data, what data we have given here, right? So that way, these two are selection line. This is the input, and so there are total 3 inputs. So we have total 8 combinations. And here we have this all the outputs. Output will stand from this Y3, Y2, Y1, Y0, right? And so let me also put a line here to separate it out from this the bottom part. So let us write all different combinations, and then we'll come back to it, like why we are writing to this. And you know that, right? Because this S1, S2, and along this D, they can take any combinations, right? Like any of these 8 combinations. So let us write all the possible combinations first, and then we'll think what will happen to this output. 1 0 1 1 1 0 1 1 1. So eventually we do not need that much space here. So this much space is enough. Okay. Now, could you please tell me what will happen for this combination? What will be the output?
Sir, all zero.
All zero. Why?
Sir, because D is zero.
Yes, D is zero because see
Sir,
first,
input is 0.
right, input is zero, and then also the selection line, right? Selection line is like 0 0. That means Y0 is selected, right? So whatever is in this D, that should go to this Y0, but D itself is 0, so Y0 would be 0, right? So all this would be 0. Okay, now let us go to the next one here.
Sir, why not will be 1? And
Y0 would be 1. Very good. What about the third case?
sir, all 0.
All 0. Because here for first the thing is the data is 0. When the data is 0, obviously what whatever will pass to this output, that will be 0 only. So that way you can also see, you can also clearly write that it will be all zeros only. Okay, here for the fourth case,
Y1 is one. Other is zero.
Y1 is 1. Here Y1 is equal to 1, right? Rest of them are 0. Okay, similarly here the data is 0, so everything would become 0. For this one, this is data is 1 and the selection line is saying 1 0, so that means it will select Y2, so Y2 will be equal to 1 and it will be equal to 0. And then this one, like for this again data is 0, so whatever the selection line will be selected, that will also have the value 0. Now for here, it is 1 1 selection line, that will select Y3, data is 1, so 1 will be passed to Y3, right? So we need to construct a detailed circuit that will perform this demultiplexer operation, right? So what we need a circuit for Y3, we need a circuit for Y2, we need a circuit for Y1, same as for Y0. So let us do them step by step. Okay. So what will be the circuit for Y0? Let us start from here. Please tell me, what will be the expression for Y0? From there we can find the circuit. Expression of Y0. Please clearly tell me quickly.
X1 bar S1 bar S2 bar D.
S1 bar, S0 bar, then
D.
D. Very good. Okay. What would be Y1? Y1?
S1 bar,
Sir,
S0, D.
S1 bar,
Right.
S
So
not.
for Y1, we have to see which data is 1. So this data is 1. So we have to take all like this combination. That is S1 is 0. So it will become S1 bar. Then S0 is 1. Then it will become S0. And then here D is 1. Right. So D is will be equal to 1. Okay. What about to Y2? Can you tell me quickly?
S1
Y2,
is bar, D.
S1 is not bar D. Y3
S1 is not D.
is not S1 D. So here it is clear, right? For all the cases, the D, the data, okay, that has no bar, right? Because obviously, then only we'll get 1 here, right? Otherwise, there should not be bar on for this D, right? Okay. Now, can you make this circuit?
Sir,
We
D
can
is common in all the gates.
D is common in all the gates, okay? Then, yeah, that is correct. So,
Sir,
yeah,
sir, why can't we simply just use 3 AND gates and construct the circuits for every Y output?
yeah, 3 AND gate you can use. And we are going to use 3 AND gate only. My 3 input AND gate, right? That's what you are saying, no?
Yes, sir. So
D.
we just take the Boolean expression and then add the appropriate knots and then just use 3 input AND gates for
Okay,
the output.
right. That's only we are going to do. Okay. So it is S1 bar, it is S0 bar, and it is D. You are saying this one, no?
Yes, sir.
Haha. So this is fine, but if you draw it like this, it's quite easier to draw, but like it seems. Look, I will. Okay, let me explain to it after I let me draw it, and then this is Y2. So it is S1, S0 bar D. So similarly, Y for Y3, it would be like this. S1, S0, SD, right? Okay, this is fine. No issue in that. Eventually, when you draw it in a, suppose like you need both S1 bar as well as this S1 and S0 bar, right? And also you need like S0 and S0 bar, right? Many times what has been shown in the circuit, like where from the data are coming. For example, let's say that we are using this AND gate only, and this is for Y0, and this is Y1, this is Y2, and this is Y3, right? And you have these selection lines, this S1 and S0, right? So let us first draw this S0, right? So this S0 will, let us draw it like this. S0 will come like this, right? And we also need S0 bar, right? So let us put this S0 bar like this here. And then let us take this S1 in green, S1, and this is S1 bar. Fine. Okay. Then we have the data input, that is D, right? So you can take it from anywhere. Let's say that we are taking this data input from here. Okay. So this is this data input D, right? And let us now connect. So you know that D will be connected directly to all these gates, right? So basically what we have done here, it is not different, but it will give you type of some idea like basically how much the circuit or how many wirings you need really have to use in this particular circuit. For example, for this Y1, you see both are like bar has been connected. So this bar has been connected with this. Okay, for Y1, this S0 has been connected. This S0 has been connected. Whenever you are doing and you have some crossing like this, so use this type of like bubbles, okay, to indicate that here only you have the contact, not here. Okay, then for Y2, you have this S0 bar again. So Y2, you have this S0 bar again, and here it will again get altered. It will be connected like this, right? Similarly, for this S1, for S1, it is this S1 bar that was connected with this, right? For the next one, it is also S1 bar, right? For the third one, see, for the third one and the fourth one, it is only this S that is connected, right? So basically, what we have done here is not at all different from this, right? But this gives more type of circuit and wiring idea, like how much wiring we have to use and how probably we can design if you are designing suppose in a breadboard, right? That will give you much better idea like how you can do it. But if you are drawing it like this, it's absolutely fine, no issue in that. So I hope now this demultiplexer part is clear to you. Any doubt in demultiplexer?
Sir, will it make sense if we send input 0?
Uh, yeah, it makes sense.
It will always give 0 irrespective of selection line.
Right.
So why will we give input 0? Because we don't get
Because
output.
in digital, suppose if you want to say send some information, suppose you want to information 5 over the channel, which is 101, right? Then obviously you have 10 in between, right? Suppose if you want to send 111, that is a 7, then I think there is no 0, right? But if for any like to represent any information in a binary, right, this 0 will definitely come, right? Then
So,
it is
but that 0 will be output for all outputs, right?
yeah,
Why not?
all output. But you know that for which selection line you have selected, right? For example, when you are suppose if you are sending the data this 101, okay, and over the channel and you want this 101 to be delivered here, right? Then first you have to transfer 1, you receive here 1, then you have to transfer 0, so you receive 0, then again you have to transfer 1, then you will get 1.
Sir, here we are selecting the output from internal, not from external, right? So the outputs will
No,
be.
not internal, not internal. The selection lines are like it depends, like up to you actually. You know where you want to connect this data for at a particular moment. You see here, the selection lines are okay in your hand only. Okay, so where you want to, you give the values here. For example, you give the value this 10, right? Then Y2 will be selected, and whatever the data you are passing here, that will be passed to Y2. And data means not only one bit, right? Because it can be a sequence of data, right? And depending on the selection line, you know which line at the output to look at. So whatever the data you are expecting from here, that will be coming from this data line only.
Sir, in the example 101, sending input 101. For 0, if we select Y0, but we will get 0 at Y1 also, right? So it
So
doesn't make.
that isn't it like expected if you are sending 5, then at this output also you are getting 5. And suppose if you want to omit 0, then you are getting only 1, which is 3. So you have sent 5 and you have received 3. So that is wrong. Na?
But sir, when we select zero y0, we will get 0 at y1, right? So it will again give 5.
Could you please repeat?
Y0.
When you select y0, okay, when you select y0, that means the selection line would be 0 0. Okay, then
Sir, I am saying like this. For
hmm,
1, we select y1. And for
for
0,
no 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 for one of what? Here there are so like put
sir,
D,
we are giving
S1,
input
S1.
101. We are
Uh,
giving input 101.
input is 101. Okay, fine.
First, we will send 1 to y1.
First we will send y to y1. Okay,
1 to y1.
okay, 1 to y1. Okay, so during that time selection line value is 10.
Yes, sir.
Okay. Oh,
Then
sorry.
0.
During that time selection line value would be 01. Yeah.
Then we need to send 0. I will select y0. But that 0 will also affect in y1 also, right? Because
Zero, yeah, zero should affect because now you have changed the data line. So if you have changed the data line from 1 to 0, then that should also reflect at the output. And now you have selected the output y1. So definitely whatever is the data that should be transferred to y1. And if y1 previously was 1, now it should be become 0.
here I am saying whether, I mean, although we don't select y1, we will get 0 at y1. So it doesn't matter whether we select y1 or not when the input is 0.
I understand. Like you were saying, by default it will be 0. See, it is for any case, na. See, any digital circuit, if you let's keep it, you will get 0 voltage, right, at all the terminal. So that means it is the logic 0. So that is expected, right? If you say it will take an AND gate, okay, you just apply at one, suppose two input, and here it is floating. So obviously here you will get a 0, right? But if you apply here 0, then also you will get here 0. Right. If you do not apply, it is 0. But the thing is that what is important is you want to send some data sequence and you want to get the data sequence here. And for binary data, definitely you will have some 0 at some point, right? So that 0 should be also reflected in the output.
Okay.
Okay. Okay. Then let us go to a new topic. New topic means actually a part of it, which is called encoder. So we have learned about decoder. Now we are learning about encoder. So you recall what was a decoder? So decoder, actually from decoder only we had come to this demultiplexer, right? So let me show you once again. Decoder. So what was this decoder? Oh, yes. So decoder here, it was like it is like 3 to 8 line decoder. Here you have 3 inputs, right? Depending on the binary value that you gave at this input. So one of the line will be selected on one. For example, if you give this first one 100, right? Then it is basically 4, right? 4. Then this D4 will be selected, right? Here it is 111. Then this 7 will be selected like that. But what an encoder will do, encoder will be perform the opposite operation of this decoder. So that means you can say like here you have these 8 inputs and you have these 3 outputs. Okay. So depending on which one you are making high. So for example, if you make D4, if you supply like if you make D4 equal to 1, means logic 1, and remaining other like output, I mean other inputs you make a logic 0, then at this output it will become 1 0 0. So it is the opposite operation of this decoder. You just flip it. This now will go to the output, okay, and this will now come to the, means this will now come to the input side, and this will now come to the output side. So let us see that. It's pretty easy only. So let us say that the same thing here, but let us draw it. let us say that we have this 3, 4, 5, 6, 7, 8. Okay, so D0, D1, D2, D3, D4, D5, D6, D6. This one is D7. Huh? D5. Let me write all the things on the end. Okay, and here we have in the output we have this 3, which is X, Y, and Z. Right. So it is basically what? It is 8 to 3 line decoder. Sorry, encoder. 8 to 3 line encoder. So here, depending on which of this input is equal to 1, and at any moment only one of the input can be 1. Okay, so suppose you want you make this D3 to be 1. So when this D3 you make 1, remaining all other inputs are 0, then the output will produce the equivalent of this D3 in binary, right? So that means it is basically D3. So it is 0, 1. And remember one thing here, we are writing it terms of like X, Y, Z. So X is here the most significant bit, and L is here the least significant bit, right? So it will produce 0, 1, 1. So it is 0, 1, 1. In the other case, suppose you want to make this D6 to be equal to 1. So D6 equal to 1. So that will produce, this encoder will produce 6. That means 1, 1, 0, 1, 1, 0. Okay. This is just the opposite operation of this decoder, right? So, or in other way, can I not say this thing will be this particular circuit or particular it is not actually circuit, it's like a black box, but what the circuit is performing, this black box is performing that operation, can we not say it as octal to binary? Please check, can I say it as octal to binary encoder?
Yes, sir.
Right, basically octal means you can have either like from 0 to 7, right, maximum this 0 to 7. So you make any one of the bit as 1, that will produce what is the equivalent binary at this output. So it is basically octal to binary encoder. And suppose you have to make the circuit, using gate, make the circuit in gate level. Okay, then can we do that? Right. So for that, whenever we have to make a circuit, we always need a truth table. So quickly then do the truth table for this. So here the inputs are D0, D1, D2, D3, D4, D5, D5, D6, D7, D7, right? Yes. And at this output, what we have is this X, Y, Z, right? So here, what we have to do, so when the selection, suppose when the selection line, this is 1, I told you, we have to make sure that remaining other lines would be equal to 0, right? So when this is the case, so what is the expected output? Can you tell me?
0, 0, 0.
0, 0, 0. Very good. Now the next case for this, I guess this. right? So let me, whenever I have started writing this thing, so let me complete it. So it will become, okay. Now tell
Sir,
me, huh?
how can we call it octal to binary? Because we are having only 8 possible inputs, but
Huh.
octal number can have so many numbers.
No, octal means like one octal digit.
Oh, okay, okay. Means
Okay.
from 0 to 7.
It is like a valid octal digit is like 0 to 7, na?
Okay.
Right. So here, how can we make, how can we write the expression of x? Please tell me quickly. What is the expression of x? Expression of x
D4
quickly.
plus D5 plus
So
1 plus
D4,
D7.
D5, D6, D7, D4
Right.
or D5.
Right. So you have to check where these x are. Right. It is x value is 1. So here for these four values. Now here for when this is on, which one is on, means which for this as one, which of the input is has one on, right? This is on. For this case, this is on. For this case, this is on. For this case, this is on, right? So the what will be the D4, D5, D6, D7, right? Okay. What will be Y? Please tell me quickly.
Sir, D2 plus D3 plus D6 plus D7.
Okay. Z.
D1 plus D3 plus D5 plus D7.
Right. So basically, you see, it is basically the odd operation, right, between inputs, right? It's nothing else, just the odd operation. So what we have to do to get this x, just let us say that we are allowed to use, 1, 2, 3, 4, 4 input OR gates. So it is then D4, D5, D6, D7. So that will basically give you this x. Right. Similarly, you can do it for y with all four inputs, and you can make this z, right, by using all four inputs. So it will be d1, d3, d5, d7, right? So it's pretty straightforward. So the construction of an encoder is not difficult, right? Just you have to take the OR operation, right? But the things will become a bit complicated when we consider some practical case. Now, what is the practical case? Say, for this case, okay, here for like D2 is only 1, right? But it might possible that even though for this to make this simple, we have said like only one of the input has to be can be 1 at any time, but it might not be the real life scenario. Maybe in the real life, more than one input has become 1, right? Say maybe this is 1, maybe say D4 is also 1. You're getting my point. Maybe more than that, more than one input become 1. So in that case, what should that encoder do? So to solve that issue, there is something I think we will not go in more detail for that part, but that is simply called as priority encoder. Priority, PRIU. So priority encoder, what it does is something like this. Maybe I will copy this little bit part. Yeah, let's say I will copy this part. Not been copied, right? it is not allowing me to copy this. Yeah, no, I think it's good. Yes. So, oh, I think some of the term is also missing. It's fine. I can write them. Say here it is like 0, 0 is supposed to be 1, right? Okay, fine. Now suppose here this red pointed out position, right? We have here this as 1, and suppose by in real life this has also become equal to 1, right? So in that case, what will be the output? So what priority encoder does is that whenever like if see this D5 has higher value, right? Because it is D5 means actually if you see in the octal system it is equal to 5, right? So it has a higher value. So it will always take the give the priority to the higher value if the higher value is 1. So it will consider this input to be as the D5 is only 1, it will discard this it will discard the fact that D2 is also 1. So what the output it will produce will be equivalent to 5. So that means at the output what we will be getting is 1, 0, 1, which is equivalent to 5. Now suppose even in another case this is also equal to 1, right? So say this is 1, this is 1, this is 1. So in that case, right, in that case, so this D6 has the highest priority among all these things. And what this priority encoder will produce is the output equivalent to 6. So the output will become this. Right? You understand my point? So here, how many inputs? 8 inputs, right? So 8 inputs mean 2 to the power 8, right? This many combinations can happen. This encoder, the simple encoder that we have designed, that will work out of this 256 combination only for 8 combinations. Only for these 8 combinations, this simple encoder will work, right? But for the remaining other combinations, this encoder will not work, right? So in that case, we have to go for priority encoder. And obviously, while if you are making this priority encoder, then it is not that it will not be that straightforward as the simple encoder, right? But I hope that you have understood that issue, like what a priority encoder does and how the operation has been performed in priority encoder. But if you want to really do it from this 4-line to 3-line priority encoder, you might find some, like it will become a bit lengthy. So what I request you to do is you try to make 4-line to 2-line. Okay, 4-line to 2-line means 4-line to 2-line encoder. So that means it has 4 inputs, 2 outputs, X and Y, and here you have D0 to D3, right? And make a priority encoder for this case, right? Priority encoder. So if you have understood this logic, you should be able to make, because here only 4 lines, so it will be 2 to the power 4, right? 2 to the power 4 is 16. So you have only 16 different combinations. So you have to play with different 16 combinations, and depending on, like as you have seen, like then you have to write all 16 combination, and you have to consider that whenever the highest value means the higher input will become 1, the output will be corresponding to that higher input only. So you have to discard the lower values. So is this priority encoder clear to you?
Yes, sir.
Okay. So, but please do this, 4 to 2-line priority encoder. Then the next one is multiplexer. So now by this time you definitely have some idea about what a multiplexer does, right? It is basically the opposite to that of a demultiplexer, right? I think we have also drawn some images somewhere, right? Let me just check it. Like to give you an idea what a multiplexer and demultiplexer does. Yeah, not here. Yeah, this one. So this is basically an multiplexer, right? So here you have so many inputs. So there, but the outputs are always less than these input lines, right? And depending on the, like, again there will be some selection lines here. Okay, depending on the values of selection lines, only one of the input will be connected with the output, right? So at a moment, for a particular value of selection line, only one of the input will be connected to the output. So let us try to implement that and see what is the, like, how, what is the basic circuit of this, and so also a couple of other operations, using this multiplexer. So multiplexer sometimes is also abbreviated as MUX, MUX. Okay, so to make the things a bit simple, let us first try to construct 4 cross 1 MUX, 4 cross 1 multiplexer. So from the name itself, it is clear that this circuit will have 4 inputs and 1 output, right? 4 inputs, like we can say their name as this input I0, I1, I2, I3. I am using because it is, these are inputs, right? And this is this output, and we say this output as Y, and we have this 2 selection lines. So how many selection lines would be there?
2.
Very good. So 2 selection lines would be there, right? So this is basically, and 4 cross 1 marks. And how does it look? You can see it here, right? So this is basically a block diagram, right? But if you have to really construct that, right, then let us also see that how to construct it. Means in the circuit level, I mean a gate level construction. Okay, right. So again, for to construct it, we have to make the function table. So it is not called as a truth table right now, but it is called now as a function table because it will show for what input values, what will be the value of output. So here let us write this S naught S1, and this is the output. So for different combinations, like only 4 combinations can possible with 2 inputs, right? So when this 0 0 line, so when this selection line values are 0 0, then obviously I0 will be selected, so the output will be I0. And for this 0 1, I1 will be selected, I2 will be selected, I3 will be selected, right? So can we make a quick circuit that which performs this particular operation? Yeah, how to approach?
So we take 3 input OR gates.
Or gates or AND gate?
AND gates.
AND gate, right? So how many AND gates we need? How many AND gates we need? 4, right?
Yes, sir.
4 only, no? So with definitely with each of this with each of this AND gate, we should have connected one of the input, right? So we have connected one of the input within it. Okay. Now tell me, what else will be connected with this AND gate?
S1 bar, S not bar.
S will be connecting S not. S not, only S not. It's not bar.
And
S not
S1
bar.
bar.
S1 bar. Right. What will be connected with this? Second one.
S1 bar and S not.
S1 bar and S not. Third one.
S1 and S not bar.
S not bar. Fourth one.
S1 and S not.
S not. S1 and S not. Right. Okay. So is our circuit is fine? Like, will this circuit work now, or do we have to do something else?
So we need to join all the.
We have to use AND OR gate, right? Like whenever any one of the output of this AND gate become 1, at this output we should get 1, right? So this is basically the circuit for this 4x1 mux multiplexer, right? So if it is now a bit complicated, if it is suppose 8x1 mux, I hope you should be also able to design that circuit. Right? Okay. Then quickly let us move to the next part. Using marks only.
So the students of the chemistry department have a test today, which starts exactly at 11. So if you could
I think, see, this is today's last class, right? So, okay, please, you can leave at your convenient time. Okay, no issue in that. Maybe I will take this up to 11 o'clock. Okay, so, but if you want to leave bit early, it's fine. So you can see the recording later on. Okay.
Okay, sir.
Okay, no issue in that. So here, suppose you have a function which is represented in product of in sum of products, and it is given in this form. Okay, and you are asked to implement this function using a 4x1 mux. Any idea how can you do it?
So taking a mux over the inputs 1, 2,
Huh?
1, 3, 6.
Okay, okay. So like, so basically here it is clear, right? When this A, B, C, like there are 3 inputs, right? So basically A, B, C, there are 3 inputs, and you have, and this is the output F function. So just why not let us write the complete let truth table corresponding to the function what has been given here. 1 0 0 1 0 1 1 1 1 1 1 0, right? So here what has been given is for 1 it is 1, for 3 there is 2, there is 3 1, 3 it is 1, for 5 it is 1, for 6 it is 1, right? Remaining these values are,
Sir, for 7 it is 1.
for 7 it is 1, but here it is 6 na?
6, sir.
6 only na? This is 6 na?
Okay.
Okay. So right, so this is this is what, this is nothing but what we have written here, like the same function, right? Now what we have to do is like, okay, maybe we are also aware of these mean terms, right? These are basically mean terms, right? You remember, I hope, mean terms and max terms. So these are
Yes, sir.
basically mean terms, right? So mean term, this is 0th mean term, this is 1st mean term, 2nd, 3rd, 4th, 5th, 6th, 7th, right? 7th mean term. Okay, so we have written this part as well, right? Okay. Now we have to we have been asked to implement this particular where is my cursor? Yeah, implement this function using a 4x1 mux. So let us also draw this 4x1 mux. So it is 4x1 mux. So it has a 4 input line, 1 output line, 2 selection lines, right? Now let us say that we have decided that we will give B and C, right? This B and C in this put in the selection line. So we have fixed this B and C for the selection line, right? This is the function F, which is expected to be produced from here, right? So when you have selected this part, right? So this B and C, these 2 lines we have fixed. So A is now that we have to connect somewhere. So already B and C has been fixed. So A will we have to connect somewhere at this input side, right? Now you will see that where should we connect this A. Okay, for that one more thing we have to do, we have to write something is like this. I feel the time is less a bit today. Okay, so we will write here I0, I1, I2, I3. Okay, then we will write here A bar, A0, A bar and A. Okay, just you will understand why I am writing this thing here. Okay, now see, A bar, right? So where we do have this A bar, we have A bar for all possible these four cases, right? This A means A is equal to 1. So we have A equal to 1 for all four these cases, right? So what we will do for, we will write the min terms corresponding to A equal to 0. So here, so for example, it is 0, it is 1, all right, it is 2 and 3. So for all three cases, the A value is 0. And for from 4 to 7, these values are 1, 4, 5, 6, 7, right? These values are 1, right? Okay. And okay, this is whatever we have like we have written this from here, up to we have got this. Now one more task we have to do. We have to see now the output. So at this output, we have to find where the output value is equal to 1. So the output value is 1 for here, and this corresponds to the case where the min term is 1. So min term 1, we have to make a circle. This min term 1, we have to make a circle here. Then here, that is min term 3. So min term 3, make a circle here. Here, min term 5, make a circle here. Min term 6, make a circle here. Min term 6, make a circle here. Right? Then the next step would be to identify, see this, see these corresponding inputs one by one, and we have to perform some operation. So for example, if you see this I0 here, for both this like for I0, like see this both values of A and A bar is not been circled, right? If none of this value is been circled like this, then we have to write 0. Okay, we'll understand why I am doing this. When we go, when we complete this and go back. Go back means look this from now from here. Okay, but first try to understand the logic or the process what I'm doing. If none of them is circled, then you have to write 0. Both of them are circled for I1, so I1 will be always equal to 1. For I2, this A is being circled, right? Only one of them circle, and the circle position is for corresponding to A. So you have to write here A. For I3, only 3 is one of them is circled, and the circle corresponds to A bar. So you have to write this A bar, right? So that indicates this with I0 at I0 input. So this is basically I0 input, I1 input, I2 input, I3 input. So for input I0, we have to give 0. For input I1, we have to give 1. For input I2, we have to give A. For input I3, we have to write A bar, right? So now this particular marks is implementing this function, this particular function. Now, if you try to trace back, like why we have done that, and really it is happening or not, then maybe step by step we can check. See, here what we have done, I think you have, see from here, this I0, right? I0 we have connected with 0. I0 we have connected with 0. Why so? Because I0, see here, there is no term for this I0, right? So I0, that means if you like, no need to connect anything with I0, because I0 will never be connected with the output, right? Okay. Now see, for this I1, right? I1 we have written here 1. Okay. I1 we have written here this 1. That is because, see, for any value of B and C, say B and C can take what values? Okay, B and C can take values like, say, 0, 1. Okay, say, for example, we can say it here. B and C can take 0, 1, Just a minute. Yes, so now we have to think for this I0, I1. Okay, what is okay? Before that, both selection, maybe one of the single selection. Let us see. So for I3, okay. So for I3, we have connected with A bar. So for I3, we have connected with this A bar. Now we have to think like why we have done that, right? Okay. So for I3, I3 is this one. We have connected with A bar, right? That is because, okay, can anyone guess why we have connected I3 from this? Can we connect it from this to this? Can we connect this?
Sir, I3 corresponds to minterms 3 and 7. So
I3 corresponds to me. No, I'm saying, yeah, I3 corresponds to minterm.
Minterm 3 and minterm 7. So the output is just opposite of A in
Opposite
those
to
two.
that of this A1, right? Yeah, exactly. So you can see here A value is 1, right? Here the output is equal to 0. So it is basically A bar, right? And you can see from here, right? It is this is 0, A value is 0, right? Here this at this F, what you are getting is this 1. So basically it is A bar, right? And please tell me why you have chosen only 3 and 7.
So because BC sum is 3.
BC sum is 3. Right, exactly. BC sum is 3 because here you are writing this one as a 3. Right? Okay. Now can you explain for 6? Yeah, can we explain for 6?
Sir, 6 and 2 both have I2 as output. So the output is same as what A is.
You are saying these two, right? And here, whatever is this wave value, you are getting that at this output, right? Okay. Now can you explain this one? I1.
Whatever may be A value, it is true.
Whatever may be a value is true, but where from this truth table you can see that see this.
When BC
Minterms
is
1 and 5.
When BC is
1.
both B and C are 1. Are you sure?
No, sum is 1.
Sum is 1 means?
C is 1.
Yeah, means the binary equivalent of BC is 1.
Okay. So when these are on, then we have this 1, right? So yeah, I think it's already 11, but I should have done one more or okay, maybe quickly from here. Suppose here we have chosen to do it like this, right? But we could have chosen the other way, na? We could have chosen this that we will connect here, say AB, right? And C will be somewhere at this input, right? Now, can you then tell me what will be the this input for inputs? Quickly. So here the inputs are C bar.
I0 will C.
Right. So you have to find so where the C value C are having 0 value, right? So C value you can see for every alternate cases, right? So C value is 0 here, C value is 0 here, 0 here, 0 here. That means 1, 3, 5, and 7, right? So it will become 1, 3, 5, and 7. So the remaining cases like 2, 4, 6, and 2, 4. No, I think 0. 8 will never come, right? How can I write 8? So it will become 0, 2, 4, 6, right? Okay. Now again we have to see where from where these outputs are equal to 1. So the outputs are 1 here.
So C and C bar should be swapped, right?
C and C bar should be.
So in minterm 1, C is true, but in the table it's written C1 has minterm 1. I mean, the first row should be 0 to
Okay,
4.
okay. Right. Yeah, I was trying to do hurry and this was a mistake. Yeah, you were right. So it should be 0, like you are correct. This is 0, right? And this is the 2, this is 4, this is 6, this is 1, 3, 5, 7. Is it fine now?
Yes, sir.
Okay. Now you have to make again for circle. The output is for 1, it is okay. Then for 3, yes. Then for 5, yes. Then for 6. Okay. So what should I write? Please tell me quickly and we will end here. So what should I write here?
C bar.
Should it be C? Because C we have taken as this input, no? Okay. So it will be C, 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 C bar. Okay. So that means we have to write here this C, C, C and C bar. Right? And please again try to verify this thing like what we are writing and why this is happening. Okay, from this truth table. Try to understand it, correlate it. So you can see definitely from here that it does not matter like which selection line or what you are going to use in this selection line, right? You can use any arbitrary things in the selection line. You could have used like we have here used here AB, here BC, you could have used AC. But while making this, making this table, you have to be careful. Okay, and maybe after that you can do a cross check quickly. For example, say like put the value of AB equal to 0 0. When AB equal to 0 0, C should be selected. So you can see from here when this AB equal to 0 0, C is 0, so that 0 is coming. Okay, so you can see from here. Okay, right now when A equal to again 0 0, A equal to 0 0, this like A value is equal. No, we are seeing now AB value, right? So again, this AB 0 0, C 0, the output is 0. Now AB again, it will never become 0. Now say AB become 1 1. So when this AB become 1 1 is for this case, right? Here, when this AB become 1 1, then this C bar will be selected, right? And what is the value of C? C value is here 1. So 1 bar becomes 0. So output is 0. So F is equal to 0. So you can see that it is basically means we can correlate always with this table and this design. So I think with this we will end here. I have taken a couple of more minutes. But again, thank you very much for your patience and understanding. So with this, okay, we will end our syllabus here. But I would also like to have, I would like to organize one doubt clearing session if you have, maybe on Saturday and either on Saturday or on Sunday for some time. But if this is completely optional, if you want only. If you want, maybe I will send an email type of poll email. So depending on the opinion of yours, I will try to schedule that. If you do not want, it's fine. But remember one thing: next Wednesday we have exams. One exam will be the written exam. Written exam is from syllabus will be from OPAMP, MOSFET, and then digital, and followed by there will be an exam which is an MCQ type, which will be conducted in Moodle platform, and the syllabus will be the complete basic electronics syllabus. Okay, so with this, I would like to thank you once again.
So,
yeah.
Like yesterday, you told you'll be sending the mail for the compensate.
Yeah, I will have it today. Okay, after this, I will upload all these things, and I'll come for compensatory email or exam also. I will send an email. Okay.
Okay, sir. Okay,
yeah. Yeah, today I will send that. Yeah.
Thank you, sir.
Yes, you are welcome.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yes, it's nice to nice to be with you for last semester, and thank you once again.
Thank you, sir.
Thank you, sir.
Mr.